So this is the grammar I have. Of course, since these are recursive rules, eventually you're going to have VP, like one VP will be so something like this. This is V prime, this is M prime, this will be X, Y, X, Y, because this is the functor. And eventually you're going to have some lexical entities like so, and then I'm going to say so that so is a two-argument function. And this just projects this. When you see so, you're essentially projecting, well, just give me the meaning of so, and I'm going to project it. This one is going to apply y to x. So you can see if you do the if you do the lambda calculus gymnastics, you're going to see that when VP rule applies V to NP, it's going to substitute for the first x, and then this is going to substitute for y eventually. So if you draw the syntactic tree for I saw the man with the telescope, what you're going to get is essentially, let me just draw you the tree because it's easiest to follow, and then I'll show you what we mean by interpreting this under uncertainty. So in one interpretation, it's going to be EP and let's say this is I, and this is so the man with the telescope, so it's going to be EP, PP, and this will be V and P, this will be so, this will be let me just draw a simple thing, because I'm not interested in internal structure of domain. I can simply write it like this. That's usually a convention. You draw a triangle if you're not interested in internal details. And this rule will be something like P followed by an NP, with the telescope. So if this is with kind of thing, this will be the preposition headed by with, which is with, and then this is the telescope. Okay. So this interpretation is where I do the seeing with the telescope. Look, domain is not modified by a VP, by a PP. So domain doesn't have the telescope. Seeing is done by with the telescope, because with the telescope is modifying seeing. Look at the sister of PP. It's the VP. So this is what is being modified, and the VP is saw the man. So I saw the man, and I did it with the telescope. Okay. So the man doesn't have a telescope, and since I do the seeing with the telescope, presumably I had a telescope. But that's not the point I'm trying to get at. This is one interpretation where we're applying many rules. Okay. So the probabilistic interpretation of this is going to look like this. Well, we're going to talk about this is the joint probability of 3t and sentence S. But S is this sentence, and I'm going to explain what joint probability means to the extent that we need it in class. But this is the sentence, and I'm trying to see, but let's call this the tree, T. Okay, the whole tree is this. So the probability of T, joint probability of P, is essentially multiplication of I mean, if T is this particular tree, this is multiplication of essentially probability of let me stick to to convention. So you can write it like if you want to write it in bottom-up fashion, you probably write it probability of S given NPVP. So this is that rule. Probability of VP given VPPP times probability of VP given VNP times probability of PP with given P and P. And these are also rules, so I'm going to write probability of P, probability of V given so times probability of P with given the word with as the right hand side times this dot is for the and man and the telescope. So essentially the probability of this tree given the sentence S and here I should clarify, by sentence S I mean I saw the man with the telescope. So probability of a tree given the sentence is essentially how I created the sentence, how I generated the tree for the sentence using this grammar. So it'll be and you can see these, you can see the correlation of these things to PDA action. Remember how the PDA worked? It recognized the right hand side and it gave you the left hand side. Well, this is given NPVP, in other words, the right hand side, what is the likelihood of it? And this is given this right hand side, what is the probability of this? These are called conditional probabilities, and this is called the joint probability. And I'm going to explain what that means soon. I'm just giving you a flavor of how things are coming. I'll probably wrap this up second week, but I mean next week. But the idea we're trying to get at is we're trying to connect rule action, like given this in the PDA rule syntactic action, I do this. Okay. And so the whole point, so I can sort of write this as a formula like this. probability of a tree given a sentence is product of probabilities okay, of that sentence, and you can conditionalize this. So the rule is something like AI goes to beta. So the way I wrote it, given the right hand side, so this is the left hand side. Okay. So given the right hand side, because that's how my PDA action works, what do I do with this? Okay. This is actually let's add more conditions to this, because although we want to get this, we want to get this in like probability of this in this sentence uttered in this current world. Whereas you told me I saw the man with the telescope, but you said that in a world where, well, like I have the telescope or the man has the telescope. So when you conditionalize this, this is going to be like product of probabilities. This means just product of everything. Product of like probability left hand side given the right hand side plus the sentence plus the world. See? So every step of the way, these are conditioned under, well, I'm doing this, this is the sentence, and this sentence is uttered in this world. Okay? So that's what we're trying to get at. In combining uncertain reasoning with highly deterministic and very tightly knit syntax semantics connection. So these are not contradictory. I mean, you can say a structure is very deterministic. Given the structure, it's very deterministic. What syntactic rule to apply is known. What semantic rule to apply when you know the syntactic rule is certain. But the world itself is not certain. So you're going to interpret these things in different ways depending on the context. So these probabilities are essentially the input to the models where you train your grammar with these tendencies of interpretation. I use this rule for this sentence in this world, and that gives you biases towards like certain sentences using certain kinds of rules under certain contexts and things like this. Okay. So for us to be able to do that, we need to know a bit of probability. This is a conditional probability. This is a joint probability, and as you can see, they are related under certain assumptions that I'm going to talk about. So we're going to do that bit by bit. But this is the idea we're trying to get at. We know how to recognize a sentence. We can draw trees, and these trees are generated by the parser, the PDA actions. And these trees have semantics because every time I do the PDA action, I do the semantic action. So I know this much, I know, but I don't know how to interpret that under probability. So we need to talk about a bit of these. So I'm going to do that bit by bit. So what are these probabilities? Well, what are the probabilities? Probability theory is a very much at the foundation of inference under uncertainty, and we need to be we need to be careful about what kind of probabilities we're talking about. You can talk about classical probability theory. With all these independence assumptions, the probability definition, and you can also talk about non-classical probability theory. This usually means something like von Neumann probabilities. Sometimes also known as quantum probabilities. I'll show you the difference between classical probability and non-classical probability as we proceed, but both are relevant to cognitive science. It's just that we know how to deal with this more than that one, although this is catching on, especially in decision theory. And the classical theory itself divides into a sort of an externalist view of probability. It's called frequentism. Frequentist probabilities. In other words, you just count the frequencies in the world as a measure of probabilistic events. And then by looking at combinatorics and possible combinatorics, you take frequencies as a measurement of probability over all sample space. Or you can do the Bayesian approach, sort of sometimes non-frequentist probability. So this is externalist in the sense that you just keep counting event structure, occurrence of events in sample space, and you just divide number of observations to total possible observations, and you get your probabilities. Whereas Bayesian inference sees probabilities as belief update, or degrees of beliefs. So for a Bayesian, a probability is a degree of belief in certain thing as a probability measure. So in that sense, it's not externalist. It's sort of belief is something you hold. So that's this basic distinction. And the easiest introduction to probability theory is probably this one. So I'm going to do that a little bit, and then probably today, but most likely next week, I'm going to tie all this up to the isodynamic telescope grammar. So that'll be like culmination of the whole course. So what are the concepts of a frequentist probability theory? So let's talk about that a little bit. Well, what is probability about? Well, probability theory is about, three things: combinatorics, prediction, and sort of inference. And all of it's combinatorics is things like, well, if you're rolling a dice, right? There are 6 possible. If you just if you're rolling a single die, then there are 6 possibilities, right? And if you're interested in like that frequentist appreciation of frequent probability, you can say, well, what is the probability of the die coming out even? So there are 6 outcomes, out of which 3 are even. So you got a 50% chance, right? So so you count the number of possibilities for like die coming out, 1, 2, 3, 4, 5, 6, and then you say, well, these are the total possibilities. And the event that I'm interested in is called is evenness. So what is the probability of that being even? Well, you count the number of even outcomes, 3, and you divide that to total outcome, 6, and you get your frequency measure of that probability. Okay, there are a lot of assumptions that allows you to make that inference, like independence, fair dice, and all that stuff. So this is one aspect of probability. So inference, this one, is sort of like, if you know an event, what can we infer from this knowledge? For instance, die example is not very good for that example. You can think of, for instance, just look at distribution of words in a language, and I say, well, I'm interested in one known fact. I'm going to take all the words that end with T. The consonant T. Given those words, what are the chances of that word beginning with a vowel, for instance? So that's prediction. Essentially, you're saying, well, yeah, I've taken these words, they're all ending with T. What are the chances of them starting with a vowel? A, E, whatever. Okay? So that's called prediction. And the inference is well, it's that's actually, sorry, what am I talking about? This is prediction. Inference is, there are two events. One has occurred, and you want to figure out two events. This is like, there's one thing in prediction, say they're all ending with T. What are the chances of them? What's the probability of them starting with a vowel? This says, well, take two events and assume one occurred. What can you say about the other one? So, for instance, let's say in the coronavirus, and the number of daily infections, it's been established that one event has occurred. Number of infections are going down. And then you want to predict another event. What is the possibility of ending the lockdown? Okay. Of course, I'm oversimplifying the problem, because the ending of the lockdown has the decision for that contains many factors. But if this is the only criteria you're thinking, you're going to take one event, namely infections getting lower and lower, and you want to tie it up to another possibility of an event that hasn't occurred yet, something like ending the lockdown. So, okay, so these are what probability is interested in, and the combination of these things will give you some inferential power over structure. So I'm going to do that by introducing some ideas in probability theory. There's some terminology that we have to go through. like what's an experiment? Outcome of an event. Sample space and event. Okay. So these are critical concepts in probability. Experiment means essentially observation of an event. Like and in case of frequentist theory, it's going to be observation of measurement. Something like nitro. Outcome is the outcome of the measurement, or result of measurement. Something like coming out 6. Sample space is all outcomes. So in throwing a dice, your sample space is essentially 1 to 6. Okay. An event is usually event is what you're interested in to make inferences, because you want to talk about events. This is called a sample of a subset of the sample space. So in my case, my interest was like coming out even. So even number of outcomes, even outcomes of throwing a die is essentially an event, in the sense that it's a subspace of the sample space of coming from 1 to 6. Okay, so these are the basic concepts that you can build a probability theory on, and I'm going to talk about discrete sample spaces for the reason that the kind of structures that we dealt with, language, vision, all of these, and planning, all of the stuff that I talked about, are essentially discrete structures. So I'm going to give you discrete outcomes. Okay. So outcome is discrete, sample space is discrete. Therefore, any subset of the sample space that is an event is also discrete. So that's the idea. Some basic ideas of probability theory. I'm trying to figure out how I'm doing on time. Introductory stuff is always difficult. So notation. There's a tendency to write the events in uppercase. And this is called the probability of an event. Okay. Some basic principles. All probabilities are non-negative. If A is in a sample space, let's say this is the sample space. Okay. If A is a subset of the sample space, then the probability of A can only be non-negative. Probability of the whole overall set is assumed to be 1. Otherwise, you're not going to get basic fundamental assumptions like cumulative functions and others. And if you have if your events are mutually exclusive, then probability of having them is the union of probabilities. So like probability of coming out even and probability of coming out odd are mutually exclusive. So the probability of coming out even or odd is the probability of coming out odd plus the probability of coming out even. And that's in this particular case going to give you the whole sample space. But it doesn't have to be the full sample space. If the event I'm interested in is like, what is the probability of coming out less than 3, then the probability is equivalent to probability of coming out 1 plus probability of coming out 2. Okay. So these are the basic assumptions of probability theory, and you have to work with these, otherwise you're not going to get your models working right when you train them for inference. So, and if this event itself has certain outcomes, okay, and if this is the outcome, the space of A, so the probability of A is the sum of probabilities of outcomes. In other words, an event is essentially characterized or described by all its outcomes. That's the only way you can characterize an event. Okay. So probability of coming out less than 3 is equivalent to having 2 outcomes, and you get that as probability of coming out less than 2. So here comes the frequency interpretation of probability, and that's going to be significantly different in non-classical probability. Now, if an experiment can come out in say n equally likely outcomes, in a sample space, if you have a n equally likely outcomes, and if a subset n of these outcomes constitute an event, okay, so probability of this event, not the outcome but the event, is probability of the ratio of these outcomes to this. So this is the frequentist interpretation of probability. Basically, you're saying I am characterizing all events by the kind of outcomes they manifest, and the way I'm going to measure this is the measurement bit is I'm going to look at all outcomes, assuming they're equal likely, and that's a big assumption. We can talk about this later. Well, we talk about this in other courses, and because that's going to be different in like Bayesian inference. And if a subset of n is characterized by u, like coming out even, coming out odd, coming out less than 3, is constitute an event, then that event's probability has the frequentist interpretation of a ratio of this outcome to total outcome. Okay, so that's a frequentist interpretation. It's easiest to work with. Here's a just for the sake of an example. Let's say event is out of all possible words you can construct out of an alphabet. I'm interested in possibility of 2-letter words. So probability of this is essentially, I mean, just assume, if you assume Turkish alphabet, let's say, we have to fix the alphabet. Right. Well, 2-letter words are essentially what? 29. There are 29 symbols. So 29 times 29 is going to give you all possibility of 2-letter words, and you divide this into let me make this. I'm trying to make this slightly more interesting. Let's say it's 2-letter words consisting of vowels. Out of 29. So I'm interested in 2-letter words in English, in Turkish, which are all consisting of vowels. That's like the more interesting event. So there are 8 vowels. So you can do 8 times 8. And you divide this out to total outcome. What are the kinds of 2-letter words that you can construct? Well, 29 by 29. So that's going to give you this possibility. And this is a frequentist interpretation of this kind of an event. Okay. Now, of course, I mean, coming back to the Turkish as an empirical phenomenon, we know that this one doesn't make sense because there are no 2-letter words that consist of only vowels in Turkish. But that's not an empirical theory. I'm just giving you how things are measured by probability theory to make inference about this. So if you have a theory of Turkish phonology, for instance, about what's a possible wordhood in Turkish, your possibilities will be a lot less than this. That's what theories are good for. It says, well, this is the huge sample space for two possible, two vowels back to back. But here's the problem with these. The Turkish phonology is such that a lot of that is just not a word. Okay, that's what theories do. This is not what that this probability is doing. Okay, it's just giving you a formal measure by frequencies of how you can do these things. All right. I'm going to do a few more things and then stop, because putting all that together, you need to look at these things first before you try to put all that in context of like influence over a structure with semantics. So I'm going to give you definition of intersectional probabilities, joint distribution, marginal distributions, and conditional distributions, and then I'll stop. Probability of two events, this one or that one, is essentially probability of A, probability of B. But since we're talking about sample spaces, if there is something common in this, what's coming to A and B is counted twice when you add, so you're going to subtract A and B. The idea being, if this is A, if this is B, and you're interested in A or B, then you add PA, PB, you're adding this bit more than once, so you take it out. Okay. So this is the idea of two events measured using measured in terms of their probabilities, and that's going to take us to intersection. What is probability of A and B? Well, it's if they're independent, probability of A and B is probability of A times probability of B. Okay, and you might remember this from the very beginning of this lecture. I said probability of a tree, since the rules are independent themselves, that's why we write them separately. You can think of that as the probability of a tree as a product of probabilities, because the rules themselves are independent in the grammar, but when you put them together, you get the probability of a tree. And of course, since you're not multiplying numbers between 0 and 1, the more rules you have to multiply, the more it's going to get closer to 0. So you have to watch out for these. I mean, in practical life, you have to watch out for underflow and things like this. And there are methods to correct these non-zero probabilities that are just too close to 0 for computers to handle properly. If this is true, if they are independent, okay. In fact, this is the definition of independence in classical probability theory. A and B are independent if probability of A and B is equal to probability of A times probability of B. Now, non-classical theory for Neumann probabilities essentially say even if A and B are independent, everything in this world is interacting, so it will be probability of A, probability of B, plus an interference element. That's where the quantum bit comes in. Everything interacts, therefore there's interference effect, and there'll be another term here for the interference effect. I'm not going to do that, but this is becoming more and more popular in decision making, because when you're making a decision and the decision is critical, you know that they're not independent anyway. So you try to, incorporate as much interference as possible to make your decision making more realistic. I'm giving you cues for more courses to take. How does that relate to conditional probabilities? Well, probability of A and B, in other words, intersection is probability of A probability of A times probability of B given A. Okay? If, of course, P of A is not equal to 0. Because if it's 0, this makes no sense. Okay? But since A and B is equal to, B and A, then this is equivalent to probability of B times probability of A given B. And since these two terms are equal, probability of A times probability of BA is equal to probability of B and probability of AB. And from here, you make a very nice leap to what's called Bayesian inference. Because if this is the case, then probability of B of B given A is probability of B, probability of A given B, divided by probability of A, assuming, again, A is not 0. Okay? So, here's how this comes out in Bayesian inference. These A's and B's, these are all events. Okay? So events are outcomes, collection of outcomes from a sample space, and I measure those events, and I try to relate them because of conditional probabilities. I'll explain what the conditional probability is. But the way this is interpreted in Bayesian inference is say probability of hypothesis given an event is probability of event given the hypothesis, probability of the hypothesis divided by probability of the event. So the whole point, this is the Bayesian sort of Bayesian take on probabilities. Okay. So what are hypotheses? The hypotheses are things like, okay, I measure something, I think this measurement is favoring sort of this model. Okay. um, and I make another measurement, I have another event. Given this event, how can I revise my model or hypothesis under the presence of this event? This is related to, well, what was the likelihood of the event given the current value of the model? What is the probability of your hypothesis in the first place divided by probability of event? Okay. So this is the sort of crucial connection in Bayesian inference. And I should probably write the names for this. This is called the posterior probability. Posterior in the sense that I revise my hypothesis given the occurrence of an event. This is called the likelihood. And the whole business of like inference modeling is essentially coming up with good estimate for likelihoods, like maximum likelihood estimators and things like this. This is called the prior. Okay, it's called the prior probability in the sense that it's not conditioned on anything. What is the probability of a hypothesis space? That's usually given by your theory. Here is my theory space. These are the possible kinds of hypotheses that you can form. They are in the beginning probably they're all uniform distributed, but somewhere a theory will give you some kind of bias over the hypothesis. You're going to say, well, given that, and then this is the probability of an event, independent of what you think about the event, about the hypothesis. Okay, and usually when you do this in Bayesian inference, because the event, you maximize or minimize something. And since the probability of an event in maximization, this changes, that changes, and that's changed, but usually the probability of an event when you maximize or minimize, it stays the same, so you can take it out, and Bayesian inference comes out I shouldn't write this as an equality, so more or less like probability of an event given hypotheses times probability of hypothesis. In other words, you're left alone, disregarding all possible outcomes of the event. You're left alone with the event and how it affects your hypotheses, and how the hypothesis makes your event look more or less likely. That's usually the modeling. Okay. So if this is constant, there is no point in taking that constant into account when you're minimizing or maximizing. You take it out and you do this. Okay. So there are three things here that I talked about, and let me just finish by mentioning them. What are distributions? Well, we have joint distributions. Okay, marginal distributions. And conditional distributions. And because notation is looks pretty much the same in these two, sometimes it gets confusing, but these are different species, so it's important to talk about them separately. Um, um, essentially, a joint distribution gives you reasoning about multiple events. Uh, um, Marginal distributions say, well, yes, I know I have a joint distribution, but I want to remove the influence of one of the events, and I just want to so there are multiple events, and you're worried about the influence of one event. Let's say multiple events like um, probability of ending the words with T is one event. Probability of beginning with A's is another event. And assuming they are independent, you might say, well, okay, I'm interested in multiple events, but I'm interested in beginning with A by removing the influence of ending with T. And that'll give you a marginal distribution. Okay. And conditional distributions is what happens to an event when you know when another event has occurred. So you observe the event. That's why you take the you take the division. In other words, you say, given this, what about this? Okay. Now, marginals look a bit like that, but they are different, right? So let me just give you so joint is something like this. Probability of this is like beginning, the event is beginning with val, E is like ending with T. I'm just making things up. So if you're interested in two different ways, so conditional could be something like this. Given that it ends with T, what is the possibility of beginning with a vowel? Okay. Marginal will be something like this. Probability of B given under the influence of these distribution. I'm interested in two events, but I'm saying I want to remove the influence of ending with T. But I'm still worried about this distribution. What can I do? Well, you can marginalize okay. You can say, well, take the joint distribution. You were interested in multiple events. You just use the same notation. Probability of beginning with E, I'm using So you can say, well, okay, you're interested in beginning with a vowel, but under the influence of a joint distribution of beginning with a vowel and ending with T, if this is what you're interested in, and look, they're different in that sense, you can say, well, why don't you just sum up all the events ending with T, and that's going to give you, under this distribution, the probability, the event space of beginning with a vowel. Okay? So joint probabilities, conditional probabilities, and marginal probabilities are different but related species. And you can see at this point that they're going to allow you to make inferences in the sense that we're going to conditionalize the rule. If you remember the first thing that I wrote, I wrote something like this. Probability of a tree given sentence I defined as probability of, using these things under the influence of a sentence. So this is the conditional. Given the sentence, what is the probability of this tree? And I'm assuming these and I do this for all the rules that I use in tree. Okay? So here's the joint probability of trees and sentences. Here is a way of conditionalizing it using the rule. So this is what we're trying to get. And you can say, well, I'm also interested in marginal distributions. What are the probabilities? What are the trees for all the trees for this sentence? Then you can see you can marginalize over a sentence and just get the probability of a tree. Okay? Overall possibilities of trees versus and sentences. So I'm going to try and connect all this next week to the way we did syntax, semantics, and computation at the same time under the influence. So we're going to add a world to this and say, okay, here's the sentence, here's the world. What is the likelihood of this? I'm going to talk about this next week. So I'll see you next week. Stay home and stay safe. I'll see you.